right, thanks Guy and Sam and Nike and Prasad and Piotr, friends, for inviting me to give this talk. So I want to tell you a little bit about sort of the learning with errors problem and its connections to various things in theoretical computer science, cryptography, and to the point of this workshop, statistical problems, the complexity of statistical problems. So let me kind of start with a party trick that a really neat party trick actually that I shamelessly stole from this work of Bruna, Bregev, Song, and Tang. So here are two distributions, right? One of them is the Gaussian distribution, and the other one isn't. Can you tell me which one is Gaussian? This is why it's a party trick. How many folks for the right-hand side picture? You're wise. I know. How many for the left-hand side? Good. So, so here is here. Let me help you out a little bit. You see it? All right. Yeah. So the distribution on the left is what's called the homogeneous continuous LWE distribution, or what has also been referred to in the statistics literature as the Gaussian pancakes distribution. The one on the right is a regular, plain old Gaussian, right? So this picture or video is super neat in that it illustrates so many things all at the same time, right? I mean, it illustrates the idea of sort of lattices, this periodic structure, learning with errors problem, which we'll see, and a sense of why it's hard, or presumably hard. We don't know for sure, right? So this is cool. So here is what I want to do in the tutorial. Before I start, let me say I'm way over ambitious. Guy asked me for an abstract of the tutorial. I think he flipped out. He's like, what are you doing? I cut it down. I cut it down by a factor of 4, right? And it's still quite ambitious. So my goal is to kind of tell you a bunch of cool things. Hopefully, some or all of them will be relevant to you in your research, right? I'm not going to get into. I'm going to make this relatively high level, right? There will be math, of course, but I won't get into the weeds. And then, of course, any questions, any point of time, feel free to ask, right? So here's the sketch of the tutorial. The protagonist for this talk is the learning with errors problem, which I'll define in a minute. And that's what I'll do. I'll show two applications of the learning with errors problem, starting with the cryptographic application. That's where kind of the problem originated from a work of Regev in 2005. I'll show some cool properties of the learning with errors problem, what's called the robustness property, which we'll again see, or entropic LWE. I'll show connections to a statistical problem, namely the hardness of learning Gaussian mixtures. And finally, if I have time, I'll show you something really cool about the learning with errors problem, which is that it has a worst case to average case reduction. So in other words, there's a theorem that says that this learning with errors problem, which I haven't defined, but trust me, it's an average case problem. If you solve it on the average, then you can solve a certain problem on lattices, which has been studied for decades, in the worst case for every lattice. This is phenomenal. We don't have many examples. We have you can count them in fingers of these kind of worst case to average case reductions. So it's really, really cool. So hopefully I'll get to a decent subset of this in the tutorial. Okay, so I'll be informal, somewhat informal. And if you want more details on any of this, there are a whole bunch of resources that I'll put up at the end of the talk. So yeah. All right, so let's get started. Let's start by solving linear equations. Okay, that's fun. Okay, so let's do that. Okay, so here is a system of linear equations. A is a matrix, right? A times S is a vector, right? N dimensions. A is m by n, so you have m linear equations and n variables, right? Let's say all these variables are integers, the equations are over integers, and so forth, right? And you have tons of equations. Okay, so you have m much more than n many equations, right? And the goal is to find the secret S, right? That's the problem. So what do you guys think about the complexity of this problem? Computational complexity of this problem. Just to warm up. Okay, so we have coffee and we have warm up. not a trick question. I certainly don't want to trick you the first thing in the morning. Okay. Well, I did already, but that's okay. It's easy. Yeah, it's easy. Well, there is a question of whether the system of equations determines the secret information theoretically, right? The matrix A may not be full rank, but that's kind of an uninteresting case. That's like I'm throwing you at the deep end of the pool, right? I mean, like if the secret S is not information theoretically fully determined, how do I expect you to find it? So if the matrix A is random, sufficiently random, whatever that means, then you don't run into this problem. And you have sufficiently many equations, you don't run into this problem. The secret is uniquely determined, and of course you can find it by Gaussian elimination, for example. Actually, I want to say there's this cool algorithm of Prasad which solves this problem, which is like unbelievably amazing. If you don't know it, you should Google it, and you should. It's not Gaussian elimination. It's really, really cool. Okay, but anyway, there are tons of ways of solving this problem, right? And that makes me sad. Okay, as a cryptographer, that's not what I signed up for. Okay, I signed up for hard problems. Okay, and this one is easy, no good. All right, so let's try to make it hard. So how do I make this problem hard? I try to lose information, right? I don't try to give you information on all the linear equations. I somehow try to lose information. Okay, so that's kind of one way to go about it. Okay, so I apologize. I'm going to be a little bit violent, right? So how do I lose information? I take each equation, the output of each equation, AI times S in a product test, right? I chop off its head. What does that mean? I lose a bunch of its most significant bits, right? Yeah, so that's one way of losing information. Does that make sense? Another way to sort of think about it is I'm going to work with these equations modulo some number q, right? That again is equivalent to modulo 10 to the 3 is like losing all but the 3 least significant digits, right? So that's kind of the same thing. All right, what about this problem? Okay, so this is still easy because you can do Gaussian elimination modulo q. Think of q as prime for a moment, without getting into all sorts of other difficulties. Q is prime, you can solve it as well. So that still makes me sad, right? Here is another way to lose information, chop the tail. In other words, take each equation and lose some of the least significant bits, right? Or in other words, add some small noise, let's say Gaussian noise to the result of each equation, right? That's kind of equivalent to losing the least significant bits or chopping the tail, as I will call it. How about that? What happens? This should be like, right up the alley of this room. Help me out. Sorry? Yes. Yes. So this is linear regression. You can solve by least squares. Done. End of story, right? So that still keeps me sad. I'm still not happy. Okay. But what turns out is that if you do both, okay, if you add an error to a small error, namely chop the tail, and work modulo q, namely chop the head, this problem turns out to be very hard. Yeah, as far as we know, of course. Can't prove anything. I mean, complexity theory can't prove anything, right? So, as far as we know, this seems computationally hard. And that is our protagonist. That is the learning with errors problem, right? So solving noisy modular linear equations, or also called learning with errors. Yeah. So is this clear what it is? Good. Very good. So let's set some parameters on the ground. There are 4 parameters of interest, right? There is the dimension n of the secret, right? So the secret comes from z mod qz to the n, right? There's m, the number of equations. There's q, which is a modulus, right? Which is how many bits do I cut off from the most significant bits, and an error distribution, which will either be a Gaussian, right? Either a discrete Gaussian, for example, or a uniformly chosen number from some interval, right? So minus b to b, let's say. Right? So these are the 4 parameters of the problem. And typically, A is chosen. The equations are chosen uniformly at random from ZQ to the n, right? The secret is chosen randomly as well from ZQ to the n. And the error distribution is one of the two. I'll keep switching back and forth between the two. In some cases, you can actually prove things like worst case to average case reductions. Other cases are actually, other examples of error distributions are easier to think about. So I'll keep switching back and forth. Okay. All right. Is this clear? So this is the problem that we are interested in. Yeah. All right. So the LWE conjecture, the learning with errors conjecture of what I gave, is that this problem is hard to solve for polynomial time algorithms. So what does polynomial time mean here? It's polynomial in n, the dimension, and m, I suppose, and log q, the description of the numbers. Right? And in fact, not just that it is hard to sort of do this always, but it's hard to find this S, the secret, even with probability inverse polynomial in these numbers. Okay, so that's the conjecture. So this problem has a ton of cool properties. For one, and I'll tell you again briefly at the end, this problem has a worst case to average case reduction, right? But other than that, here is a different problem which turns out to be sort of more useful for cryptography, which is a decisional version of this problem, right? So the LWE problem is a search problem. I give you a bunch of noisy linear equations, find the secret. Here is another problem. I give you either, on the one hand, a bunch of noisy modular linear equations, right? Or I give you just random junk, like random numbers, right? So this vector B is chosen truly at random at the bottom. On the top, it is chosen from the LWE distribution. Right? The question is distinguish between the two. Okay, so say yes one time in one case with probability epsilon more than in the other case. So remarkably, what happens is that this problem is actually equivalent to the search problem. Right? So the decisional LWE and search LWE are, essentially the same. If you can solve one, you can solve the other. One direction is trivial to see. If you can solve the search problem, you check the solution, right? That's easy to see. The other direction is much more interesting, but it's true. Right? So that's one cool thing about it. This problem also turns out to have connections to various other problems that people have studied about in like other contexts. For example, this is really exactly the problem of decoding random linear codes, right? S is the message, A is the generating matrix of a random linear code over Z mod QZ, right? And I do A times S plus noise, find the message, decode the message, right? So this is decoding random linear codes. The only difference, and actually this turns out to be a very crucial difference, is that typically when you think about sort of decoding, right, you think about Hamming errors, right? Namely, the adversary has an error budget, and the guy says, look, let me pick a subset of the coordinates and let me dump all my error budget into it. Okay? So in other words, pick a subset of coordinates, make these things sort of arbitrary or I suppose random, right? And leave the other coordinates alone. Right? It's Hamming errors or L0 errors. Here, the notion of error is different, right? You have an error budget and you spread it equally among all the coordinates. So nobody goes untouched, but nobody gets too much error, right? No coordinate gets too much error. Right? And this difference is crucial. It's really absolutely crucial, certainly crucial for cryptography. Right? The other version of the problem is referred to as learning parity with noise or learning parity with noise over finite fields, right? The finite field version of it. And that turns out to be much less useful in cryptography than this version. And we can also show much fewer things, like interesting things about that problem than the LWE problem. Okay. Learning noisy linear functions, which is learning parity with noise or its generalizations, right? And worst case hard lattice problems, which I'll tell you in more detail later. Okay, so this turns out to have tons of connections to other problems in TCS. Yes? Okay, so the not useful yet is actually a lie, right? So it seems like empirically we can build so many fewer cryptographic objects from the learning parity with noise assumption than from the learning with errors assumption. It also turns out to have less structure in the sense that, you can put the learning with errors assumption in the statistical zero knowledge complexity class, which is a subclass of NP. You can't for the LPN problem. I don't know what that says about the relative complexity of the problem. There's no reduction back and forth. So the one thing that I want to tell you is there's a very cool construction of program obfuscation, which, never mind, it's a parenthetical comment, which actually uses the learning parity with noise assumption, and the learning with errors assumption is not good enough for that application. So this is, like, it just kind of blasts my intuition kind of out of the way. So what I said is sort of our current state of knowledge, and even that is not quite accurate. Good. Okay. So there's this. This is my sales slide. Why learning with errors? So lots of sort of reasons we care about it in cryptography. This problem seems very hard, exponentially hard, as we will see in a minute, if you set the parameters right, and even for quantum computers. So take it for what it's worth. Very simple, just linear equations with noise. Tons of applications in crypto and applications outside crypto, both sort of reductions, which we'll see in a minute, but also seemingly algorithms. So this is something that I've understood much less, and I'm still trying to kind of figure out this work of Elias Zadik and the others. Yeah, so cool stuff. And there's, of course, this problem is so close to kind of statistical problems that there's an information computation gap here, right? So let me fix the dimension of the secret, the modulus, the error distribution, right, which is uniform in some interval minus PB. And let me sort of see what happens when you increase the number of equations, right? So of course, if I give you no equations, the secret is not determined at all, and I'm being ridiculous asking you to find a secret, right? So, and that keeps happening for a while, until this number, which is actually quite natural, believe it or not, right, when you have a transition, when the secret actually becomes information theoretically determined, and then I am not being ridiculous in asking you to find a secret. This number is not crazy, it's just counting, really, right? I mean, you want the number of inputs, the entropy of the input, to be smaller than the entropy of the output. And then keeps chugging along, and as far as we know, in this information theoretically unique regime, determined regime, it's still hard to find the secret, and that happens for a while until, so M here, the number of equations is about linear in the dimension of the secret. It keeps going, keeps going, keeps going, until M is like essentially exponential in the dimension of the secret, and the problem seems hard all the way in this regime. So don't worry about what those numbers are. We'll actually see. They look nuts, but we'll see. Okay. But this number should be clear. Yeah. So this is just kind of counting. Counting if I have enough equations in the presence of error and so forth. Is that clear? So let me stop here. See if there are any questions. Yes. Good. So let me give you an informal argument, right? So think about a function that maps, like S and E to AS plus E, right? Fix A for a moment. The number of possible inputs is the number of possible S's and number of possible errors, which is Q to the n times 2B plus 1, which is the number of elements in an interval, to the power M, right? So the total number of inputs is that much, the one on the right-hand side, right? And when the number of possible outputs, which is Q to the M, becomes larger, right, you expect this function to start becoming injective. This is a hand-wavy informal argument, but in this case, you can actually show that this is what happens. Right. Yeah. Cool. All right. Great. Thank you. Any more questions? Good. Let's move on. All right. So now let's kind of move along. What I want to show really is I want to start with algorithms for the learning with errors problem, because there are like 4 different parameters. Like how do you kind of set these parameters, and what choices of these parameters give you algorithms, what choices give you hardness, right? I mean, it's a bit not clear. So what I'll tell you is it turns out that there are 3 different algorithms for solving the learning with errors problem. I'll tell you 2 out of 3, right? And that'll give you a sense of where the hardness versus algorithms landscape lives, right? Then I'll show you applications of the learning with errors problem. I can't resist showing you a cryptographic application, so I'll go ahead and do it. And then a statistical application, and finally, cool properties. And we'll see how far we get. I don't expect to get to the end of it, but and I guess it's your job to make sure that I don't get to the end of it. Okay, so ask questions. All right, so algorithms. Right, so the three algorithms. There's an algebraic algorithm, and this is due to Sanjeev Arora and Ronge. There's a classic sort of geometric approach to solving this problem using what's called lattice basis reduction. I'll tell you in a second. And there's a combinatorial algorithm, which I'm not going to tell you. Right? So let's start with the algebraic algorithm. Okay, so again, let's step back, take a breath. Okay, so here's the problem we want to solve. Given A and AS plus E, right, find S. Actually, it doesn't matter. You can find E, then you can find S, right? They're equivalent. They're informationally equivalent, right? If you find the error, subtract the error from AS plus E, then do Gaussian elimination. Yeah, that's that. So how would you go about solving this problem, right? If you are an algebraist, if you are enamored with polynomials, for example, okay? So here is one way to do it. Pretty neat way. So here is a key idea. Each noisy linear equation, right? This is what you have, a bunch of noisy linear equations. Each noisy linear equation is actually a hidden polynomial equation. It's effectively a polynomial equation, yeah? Okay, so let me tell you what that means. So think about this noisy linear equation. B, which is like one coordinate of the output, right? Which is A in a product S plus E. A is public, so this is what the equation is. S is secret and E is secret. So now, for a moment, imagine that the errors are actually small. In fact, they're binary, let's say. But whatever I'm going to say generalizes to sufficiently small intervals, right? So binary errors. So what does that mean? B minus A in a product S, the sum of AISI, is actually 0 or 1. I just don't know which one it is. For each one, it's IID 0 or 1. I just don't know which one it is, right? Yeah? But regardless, I can actually write down a polynomial equation on the secret, on the secret S, or the coordinates of the secret SI, right? So B minus A in a product S is either 0 or 1. So in other words, B minus A in a product S times B minus A in a product S minus 1 is definitely 0, mod Q, right? Mod Q. So here is a noiseless polynomial equation that you got from a noisy linear equation, right? And then say, oh, good, that's fantastic, okay? Like, I removed the noise, okay? Yeah, that's great. Except solving even degree 2 polynomial equations in the worst case is actually hard. It's NP hard, actually, right? Depending on how you set the parameter. Yeah. So it seems like we actually made a progress in the opposite direction, if at all, right? Okay. So here comes idea 2. Idea 2 is that this system of polynomial equations is actually easy to solve if you're given sufficiently many random equations, random enough equations. Okay, so let's see why that is. This is using a technique called linearization, which was actually quite popular in the, which is quite popular in the cryptanalytic literature. These are bad guys who break stuff, right? From the 80s, right? So this was successfully used to break a whole bunch of crypto systems. In fact, I think there's a story of Adi Shamir, actually, or Coppersmith, I don't remember, Don Coppersmith, breaking crypto systems as the speaker was giving the talk, okay, online, using linearization, right? So this is super simple but super powerful. But what is it? So let's write down this polynomial equation up there in a slightly better form, right? Just kind of collect variables. There are degree 2 monomials, degree 1 monomials, and the constant term, right? Yeah. So that's that. So I'm going to close my eyes and pretend that each monomial is a new variable. Okay. Why not? So Si times Sj, I'm going to call it T sub ij. This is a new variable, right? Now, of course, in reality, these guys are all related. They have relations between them. Tij times Tjk is something, right? Or divided by Tjk is something, right? But I'm going to ignore it. So now you have what do you have? You have a noiseless linear equation in the variables T sub ij, right? Yeah? Does that make sense? So that sounds fantastic, actually, right? I went from noisy linear equations to noiseless polynomial equations to noiseless linear equations, right? party time. The only problem is that if you're given relatively few equations, let's say a linear number, order of n equations, let's say, or order of n log n equations, or n to the 1.5 equations, right? You now have, instead of n variables, you have n squared variables, right? Because we made each monomial into a new variable. So there are n squared variables, right? There are tons of solutions. Like if you have n to the 1.5 equations, there are tons and tons of solutions, right? And my real solution is kind of hidden in between them. It has all sorts of constraints between its variables, right, its coordinates. And how do I find it? It's sort of a needle in a haystack type of problem. Right? But the good thing is that the more equations you get, the more of these spurious solutions disappear, right? Yeah, so these disappear, 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 keeps going, keeps going, keeps going. At the end of the day, I know that regardless of the number of equations I give you, the real solution, rather the T sub ij defined by the real solution, stay. I mean, it is always a solution, regardless of the number of equations I give you, because I planted this solution in there. And each new equation kind of cuts down these spurious solutions, right? And ultimately, I'm left with just the right solution. And when does this happen? When the number of equations is more than the number of variables, roughly speaking, which is n squared in this case, right? Yeah, so that is linearization. Okay, so that's what happens. So of course, this is the idea, right? You have to show things, right? Which I'm not at this point. The real challenge is to show that these equations you get, these sort of linear equations you get in n squared variables, order of n squared variables, they're actually linearly independent, right? Or there are sufficiently many linearly independent variables that you can actually, these spurious kind of solutions actually disappear, right? So that is the challenge in showing this, but you can. Okay, so what is the outcome in any case, right? So if your error comes from if the absolute value of your error is small, right? I don't know, 0, 1, or -1, 0, 1, or whatever, you can actually solve the LWE problem given sufficiently many equations. Okay, so n to the 2b plus 1 equations if the error comes from the interval minus b to b. Okay, and this actually is the best known in this direction of attack, right? So the lesson here is that if you want hardness, as I do, you shouldn't set the absolute value of the error to be too small, right? So certainly, you shouldn't set the absolute value of the error to be too small and give away too many equations. That's a disaster, right? So you have to do one of, limit the number of equations or increase the magnitude of the error, one of the two. Okay, so this is one algorithm for LWE, right? It's cool, yeah. We don't know how to do any better, actually. We don't know how to do any better. N to the 2b plus 1 is the number of monomials when you write down the, right? So, yeah, and that's, like square root of that would actually be pretty cool.
Like n to the b.
Right, it would be pretty cool. I don't know how to do it. Right, so that in particular would solve binary LWE with linear number of samples, right? The trivial is n squared. If you get square root, then you're, that I don't know how to solve. Cool, all right? So again, the lesson is don't set the absolute magnitude of the error to be too small. Okay, so that actually explains the n to the 2b plus 1 number in the sort of the easiness regime, right? So when the number of equations m is bigger than n to the 2b plus 1, you get an algorithm. Okay, is that good? All right. Okay, so the second algorithm I want to tell you about is seemingly completely different, and it uses lattice basis reduction, and actually a relation between the LWE problem, which is actually a lattice problem in disguise, thinly disguised, but disguised. Okay, so here is a lattice. Okay, so here's a new kid on the block, right? We did learning with errors. Here's lattices. Okay, it's a discrete additive subgroup of Rm. generated by, we'll talk about full rank lattices. So in m dimensions, you have m vectors which are linearly independent over R, and these guys, all integer linear combinations of these vectors generate a lattice. Right? So that's what it is. B1 and B2, all integer linear combinations, whatever, generate the lattice. Right? Good. All right. So here is another, yeah, so this is clear, right? So sum of all integer linear combinations of BI generate a lattice. Here's another party trick. Here's the lattice basis. The columns, the two columns are the two basis vectors in R2, right? Or Z2 for that matter. What lattice does this generate? Yeah. 0, 1, and 1, 0. Are you confident? Can you lock your answer? No. No. Yeah, can you explain why?
I mean, both 1, 0, 0, 1 are, I think,
linear combinations of this, right? You can derive 0, 1 by, I guess, subtracting one way and 1, 0 by doing one more linear combination. Another way to see this is the following. You know this picture, right? The determinant of the basis matrix B is a volume of the fundamental parallelepiped of the lattice, which is this guy. Yeah. So look at the parallelogram, spanned by B1 and B2, right? So that's the volume of the parallelepiped, which is also the determinant of the basis matrix, right? This basis generates only integer points, right? Only integer points. All integer combinations of these guys, all integer points, really, right? And the determinant of this matrix is 1, actually. Right? So what could it be? I mean, these are just integer points, right? Unless this is exactly the integer lattice, the determinant is going to be a multiple of 1. It's going to be bigger than 1. Right? So it has to be the integer lattice. Yeah, that's another way to see it. All right, Kirill, I guess, I anticipated someone answering this question. What about this one? I'll keep going, by the way. The lowest entropy answer is what? Is Z3, Z cubed, right? But it isn't correct. I can tell you it isn't correct. Why is that the case? Can anybody find a sort of counterexample for why it cannot be? Why the linear combinations of the columns cannot span Z3, Z cubed? Yes?
First coordinate is even.
Beautiful, right? No matter what integer linear combination you pick, the first coordinate is even, so it cannot possibly be all integer points. In fact, it turns out that that is the only constraint, and you can generate all integer points where the first coordinate is actually even with this thing, right? So my point is, unless you're Kirill, okay, these basis matrices can be pretty complicated, right? It's hard to tell, what is the shortest basis of a given lattice. Given a basis matrix, what is the shortest basis of the given lattice? Or what is the shortest vector, even, in a given lattice? Okay, so I actually don't have more, but yeah, that's that. Right, so this is the shortest vector problem. So given a basis B in Z to the m by m, I could have written the real vectors, but just to keep my sanity, I'm going to do Z to the m by m, right? The problem is to find the shortest vector in this lattice. The shortest, a linear combination of the column vectors whose length is the shortest in the Euclidean norm. That's the shortest vector problem. Of course, 0 is always a linear combination of the columns, so you say, okay, shortest non-zero vector. Yeah? So this is a classic problem in the study of lattices. It's arguably, this problem was studied from the time of Minkowski in the 1900s, although I guess I don't know how much he thought about computation, right? He actually showed that, lattices, given a basis matrix, there's a certain upper bound on how big the shortest vector can be. There's an upper bound on the length of the shortest vector, and that was useful in like a whole bunch of sort of, if you've taken a class on algebraic number theory, this kind of figures prominently in the first few lectures. So that's what lattices were used for to begin with. And then sort of starting from Lenstra, and Lovász, people started sort of looking at the computational complexity of finding these shortest vectors. Okay, so this is the shortest vector problem. And of course, we are computer scientists, right? So when we cannot solve a problem, we change it. Yeah, so here is here's a natural approximation version of the shortest vector problem, where I don't ask you for the shortest vector, I ask you for a vector that is at most alpha times. Alpha is a number that's at least 1, right? Alpha times the length of the shortest vector. Yeah. And lambda 1 is just a notation for the length of the shortest vector. Y1, never mind. That's what it is. Yeah, is it clear, the definitions? Just to step back, we are in the middle of algorithms for LWE, right? I mean, just to make sure where we are, yeah? We'll see all this machinery, and I'll tell you how this machinery actually connects to give you an algorithm. Okay, so here is the algorithmic or hardness landscape for approximate shortest vector problem. You can imagine that as the approximation factor increases, the problem becomes easier, and the question is how easy. Alpha equals 1 is the exact shortest vector problem. It's shown NP-hard by Aitai in a work in 1996. There's a cool story behind this work, actually. Is this talk being recorded, by the way? It is. Oh, okay. I gotta watch my words. That's good. That's good, I suppose. But as a cryptographer, you know, like you tell me not widely distributed. Oh God.
I mean, you don't have to sign the thing. Well, you can decline to sign.
Sorry, what's the question? It's not on YouTube. Well, we will. We will.
Okay, so let me modulate. Okay, so.
You can turn off your mic.
No, it's okay. It's not that juicy, so it's fine. So the story behind this result is the following. At MIT, we used to have this, these qualifying exams that we used to put people through. This is before my times, and I guess the story is that you're given a paper, okay, and you have to read it in, like, I don't know, 2 weeks, 4 weeks, I don't know what time it is, and come up with an original result. Could be small, but original. Yeah, that's pretty cool, isn't it? Okay, I guess the response says it all. But it is cool, actually. So this paper was given to Daniele Miciancio when he was a graduate student here to read and understand and actually improve on, right? If you've read one of, okay, it's not the easiest paper to read. Okay, let me just put it that way. And yet he managed to actually read it, and he improved it to actually not NP hardness, but NP hardness of approximation, and he won the Fox Student Paper Award for it. Okay, so sometimes it's actually good to, so the lesson, sometimes it's actually good to throw people at the deep end of the pool. 99% might sink, but the one that floats will float. Okay, so, all right, so that's NP hardness. Is a very famous result. In fact, improvements of the NP hardness to hardness of approximation have won a string of best paper and best student paper awards. Subhash Kot had a result, and Oded, and so forth. Right? It's also recently shown to be ETH hard, actually. So it's if you believe in the exponential time hypothesis, which I'm not going to define formally, 2 to the little o n time algorithms are unlikely for the exact version. And finally, you can actually solve this in time, 2 to the n times. It's 2 to the n times polynomial in the input length, which is the length of the basis. It's a Frobenius norm of the basis. It's an upper bound on how many bits you need to write it down, right? Polynomial like that. So this you can do. 2 to the n times poly, the number of bits to represent the basis, you can do. And this is, it's originally shown by Aitai, Kumar, and Sivakumar, who just won the Stock Test of Time Award for this work. But that wasn't 2 to the n, it was something like 16 to the n or something, right? And it was improved all the way to 2 to the n. So that's what exact shortest vectors are. On the other hand, on the other end of the spectrum, the famous Lenstra-Lovász algorithm solves the 2 to the n, or 2 to the n over 2 approximate version of this problem, right, in polynomial time. So that's where this is the 2 extremes, right? And you can interpolate between these extremes. It turns out that what you can get is 2 to the k approximation of shortest vectors can be computed in 2 to the n over k time. So the exponents multiply to n, yeah, up to logarithmic factors. Yeah? Good. And this is what we'll use to actually solve LWE, this sort of trade-off algorithm. You can also improve that alpha 2 to the n over 2 to 2 to the n log n over log n, but never mind, between us, what's the difference? Good, so this is the hardness or computational algorithmic landscape of the shortest vector problem. Yeah. B is still the basis. B is a given basis for the lattice. And so actually, that cannot be correct, right? It's 2 to the n log n over log n, but OK, fine. Whatever. I can't stand this. OK, all right. OK, whatever. Yeah. OK. All right. All right. N is a dimension. N is the dimension of the lattice, yeah. So what is the, like you said, 2 to the n approximation, you're like, what is going on here? Like, why is 2 to the n interesting, right? The point is that the approximation factor is independent, this exponent is independent of the number of bits you need to write down the basis vector. So I could give you a basis that has like, I don't know, n to the 100 bits to write down, like a really, really terrible basis. And yet, in time 2 to the n, as opposed to 2 to the n to the 100, you can actually, right? Enumerating would take time 2 to the n to the 100, because you write down all possible linear combinations, generate all lattice vectors in this huge ball, et cetera, and that would be totally useless, right? So the really cool thing is that you can actually throw that away. You can be singly exponential in the dimension alone. For example, the LLL algorithm was actually turned to an exact algorithm that runs in time 2 to the n, right? So that's actually right here. So AKS actually uses LLL. And that was actually used to solve integer programs in a constant number of variables. And that was sort of a big result in the 1980s. Right. Good. So this is what it is. So here's the punchline. LWE is a lattice problem. Okay, so we can actually use all this machinery that people have developed for lattice algorithms to actually solve LWE. Right. That's the punchline. So why is it a lattice problem? So let's look at the lattice. Well, okay, so here is the kind of the intuition, right? So maybe I'll start writing things down. Right, so there's a mod q in the definition of LWE, whereas lattices say there's no modulus, there's no q, nothing, right? I mean, it's just linear combinations of integer linear combinations of things. But think about sort of this special class of lattices called modular lattices, right? These are lattices which contain the vectors 0, q and q, 0, and so on and so forth, all multiples of q times unit vectors, right? So that is a special class of lattices, right? Then, of course, you can put sort of other vectors in here, a1, a2, et cetera, of course, a1 plus a2, and so on and so forth, right? So modular lattice is a lattice that contains q z to the m. That's it. Yeah? So what is the good thing about this lattice? It is actually like you don't need to look at the whole lattice to understand its properties. You just need to look at the q by q by q by q by q, right? Because it's symmetric, right? This guy is actually implementing reduction modulo q, basically, right? Yeah. So then the LWE problem says, well, I give you a linear combination of the basis vectors a1 and a2 here, right? In this example. Plus a little bit of noise, right? This is a noisy linear point. And why don't you actually decode it to the closest lattice vector? That's the LWE problem. So that's how you write down the LWE problem as a lattice problem. Not the shortest vector problem, but sort of a decoding problem. Okay, so that's one step. The second step is sort of seeing that this decoding problem can actually be reduced to the shortest vector problem, as I'll show you in the slides. Okay. So again, let's look at the lattice generated by the columns of A minus A, it doesn't matter, B, right, which is the target, right? And this Q times the identity matrix, which is this modular lattice overlay on top of it. So here's lemma 1. if B is actually drawn from the LWE distribution, this lattice has a very short vector. Okay? Why is that? Minus A times S plus B is the error E, right? Modulo Q, but the modulo Q can be implemented by the last m columns, right? So in fact, E is a short vector in this lattice, right? That's number one. Number two, assuming that you have sufficiently many equations, right? M is at least n log Q. If B is actually random instead of drawn from the LWE distribution, this lattice does not have any short vectors. And this is this is sort of a probabilistic statement, right? With high probability over A, the matrix A, the columns of A, and B, which is random at this point, there are no linear combinations that make the result short. And that's just a probabilistic, it's just a counting proof at this point. Right? Yeah? Every linear combinations of A and B is actually random. Every fixed linear combination of A and B is random. The chance that a random vector is short is really, really small. And then we would do a union bound over all linear combinations, right? Yeah.
So what do you mean by having a short vector?
Short vector. Good, good, good. Very good, very good, very good. Because I am actually, you know, I'm working over finite fields, right? Good. So, so when I think about a vector in FQ, ZQ to the M, right? I think about its representative inside sort of, let's say, the cube minus Q over 2 to Q over 2, right? So that's minus Q over 2 to Q over 2 is Z mod QZ for me, right? So I reduce the vector to this world, and then I compute the Euclidean norm. So just syntactically the Euclidean norm. Right? In fact, actually, I don't really care about the Euclidean norm. I know that even in the L infinity norm, this vector cannot be short. So each coordinate, there's one coordinate of every linear combination that has to be large. Right? This is just a probabilistic statement. Proof is what I just outlined. Right? Yeah. So you have two things. One, you know, if you have samples from the LWE distribution, this lattice that I constructed has a short vector, right, of length equal to the error. If it's random, then this guy really doesn't have any short vector. The shortest vector has length Q over, I don't know, 8 or something with very high probability. Right? So then, yes?
So, stupid question. So if you switch to infinity, is it still Q over 8?
This is actually Q over 8 in the L infinity. Yeah. So L infinity is at least Q over 8, so of course L2. This is the easier thing to count. I don't have to count balls and so forth. I can just count intervals, right?
I mean, I guess it also matters if Q and the maximum error value are chosen. You know, so that, I mean, capital B, not the basis capital B, but the other capital B is small relative to Q.
That's right. So I have to. In fact, I am going to choose each coordinate of the error to be small, relatively small. Think about Q over 100, if you will, right? That's the regime where you have an information theoretically determined solution. That's also what is useful in crypto for the same reason, right? And so on and so forth. Yeah. Good. So here is a sort of a reduction of LWE to distinguishing between a lattice which has a short vector to a lattice which doesn't have any short vectors, right? And that's the shortest vector, the decision version of the shortest vector problem. Okay. So in other words, a Q over 8E approximate shortest vector algorithm would let you distinguish between these two distributions, right? Because I feed the
By the way, is the error given? Because otherwise, could there be an uniqueness problem with finding S?
if you know that the error is short enough, then there won't be a non-uniqueness, and the number of equations is large enough, then there is no non-uniqueness problem with high probability, right? That's right. So yeah. These catches. Yeah. So I'm always in the setting where A is random, right? And the error E is short enough. So then, you know, given sufficiently many equations, I have uniqueness. That's it. Yeah. So what happens is I take this lattice, I feed it into a approximate shortest vector algorithm, right? In one case, the lattice has a tiny vector, right? And you are guaranteed to give me a vector that is 100 times as big as this. So the only vector there is the shortest vector, right? because this vector is so small compared to all the other vectors in the lattice. So you will give me the shortest vector. On the other hand, there's no chance that you can give me such a short vector because it doesn't exist. Right? So that's how you solve the shortest vector problem, the LWE problem given a shortest vector orbital. Yeah, so the lesson at the end of the day is that for hardness, the ratio between the modulus and the noise, sort of the signal to noise ratio in a sense, right, should be smaller than 2 to the n. In fact, it should be smaller than 2 to the n log n over log n, for hardness. Right? But to the best of our knowledge, if I set this ratio to be 2 to the n to the 0.99, there is no polynomial time algorithm that solves the problem. Right? So and people actually take this literally to its quite literally, right? There's actually a NIST competition to actually standardize, lattice-based crypto systems, and they really want to push the limit to what is known to be easy, right? Leaving a little bit of margin, but yeah. Good. So that's the 2 lessons, and that gives you the second number in the on the right. Yeah, so why is that the case? So I want a Q over 2b plus 1, or Q over b, approximate solution to the shortest vector, and that can be computed in 2 to the n over log Q over b time, and samples, and that's what you get. Okay, good. That's good. So that's algorithms. And you can use these to set parameters for LWE. That's that. Okay, so let me tell you one more thing. So what this says is that you can reduce LWE to solving a lattice problem, right? So that was a pretty easy kind of at least if you ignore the actual algorithms, like the LLL algorithm, right? This is a pretty simple reduction, right? What is cooler is that the converse is true as well. If you can solve the LWE problem, you can solve the shortest vector problem, right, or the decision version of the shortest vector problem in the worst case for any lattice. Okay. That is Oded's theorem. Let me put the theorem up here. And do you think this is a time for a break, or yeah? All right, I think this is a good stopping point, maybe like a 5-minute break. But let me put the theorem up here, and then we'll continue, after we come back. 5 minutes. 10?
Just one break, right?
Yeah, just one break. Yeah. So 11:05, we get back. All right, so yeah, this is Oded's worst case to average case reduction. And what it says, I guess, is that if you just want to forget most things and take the most significant bit out of it, if you solve LWE with a modulus Q, a signal Q, and noise sigma, right? What you get is a shortest vector algorithm with approximation factor Q over sigma. So what matters really is the signal to noise ratio in this reduction, right? Up to a factor of n, but never mind. Okay, so let me move on. Let me tell you about 2 applications of LWE. I'll start with the cryptographic application. Okay. So before I tell you this application, let me tell you a cool theorem about LWE, and that's actually crucial for this to make this application work. Let me think about the LWE problem, right? A and A times S plus E, right? And what we were talking about so far is where A is random, the secret S is truly random in ZQ to the n, Z mod QZ to the n, right? And the error is either small in one way or the other, right? The cool thing about LWE is that you can change some of these parameters around, and the problem remains as hard as it used to be. For example, what turns out to happen is that if you choose a secret instead, not uniformly at random, but from the error distribution, right? It's kind of a weird thing to do, but the point is that the coordinates of the secret are actually small at this point, right? So that's LWE with small secrets, right? You would think that you reduce the hardness of you made the problem easier, right? You reduce the entropy, threw away a whole bunch of entropy from the secret, so you made the problem easier, but turns out not. There's actually, this problem is as hard as LWE with, i.e. with random secrets. Okay? This is a very, very cool reduction, which I'll show you on the board. Okay, so here's the theorem. It's by Applebaum, Kash, Pikert, Sahai. I'll show you the proof on the board. Okay, but before that, is the statement clear? I'm mucking around with LWE, right? The way I'm doing it is I'm making the secret come from a certainly lower entropy distribution. In fact, the error distribution, right? IID from the error distribution. Okay? So here's what I want to show. I want to show a reduction. From LWE to small secret LWE. Can people out there see it here? Is that okay? All right, good. So here's the idea. Let's take an instance of the LWE problem. Right? This is what I'm supposed to. So I'm showing a reduction. Showing a reduction that says if you solve the small secret LWE problem for me, I will solve the real LWE problem. Okay, so my input is an instance of the LWE problem where S is actually random. Okay? My goal is I will produce an instance of the small secret LWE problem, and I'll use your solution to solve mine. Okay, so this is what I want to do. So here's what I do. I write, let me write these, okay, so but before I go there, here's the intuition, right? So the LWE distribution, right? So call this B, if you will. You know, I don't know what the secret is. I don't know what the error is. But what a sample from the LWE distribution tells me is a way to write the secret linearly as a function of the error, and also a way to write the error linearly as a function of the secret, right? So that's apparent from here. So I'm going to use this fact. So here's what I'm going to do. I'm going to write this as, let's say, 2 samples. Okay, so A1S plus E1, call it B1. So in other words, I take n samples, the first n samples of the LWE thing that you gave me, right? So this thing is n by n. And I have a whole bunch of other things that you gave me as well. I didn't do anything at this point. I just kind of split my samples, LWE sample equations, noisy linear equations, into the first n and the last m minus n. That's it. Yeah. Now I use the fact that that E1 here, the error, is rather the other way around. The secret S is actually a linear function of the error. What is the linear function? It's A1 inverse times B1 minus E1. Yeah? I don't know either of these two things, S or E1, but I can write this equation. Now take the second set of equations and do variable substitution. Okay? So what do I get? I get A2 and A2 times S, which is A1 inverse, yeah, I just did variable substitution. Now look what happened, right? I take this guy and subtract A2, A1 inverse, B1 from it, which I know. I know A2, I know A1, I know B1. I can subtract this guy from it, right? And what I get is, and I multiply this guy by A1 inverse, what I get is LWE samples where the secret is small. In fact, it comes from the error distribution. End of story, right? And once I did this process, I can feed it to the LWE solver, small secret LWE solver. The guy will happily give me E1, and then that's all I need to reconstruct the secret S. Yeah, it's super simple. So what that tells me is that this whole entropy of n log q bits of entropy in the secret, in the LWE definition, it was irrelevant. Like most of it was not being used. All that was being used was n log, maybe like n times the entropy of each coordinate of the error, really. Right? So that's the proof. In fact, something much stronger is true. You can muck around with the secret distribution any way you want. Like choose a secret from any distribution. The coordinates don't have to be IID. Really, doesn't have to be anything. It could be an arbitrary distribution. And it turns out to be hard, essentially, as long as the distribution has sufficient min entropy. Okay, that's sort of the best you can hope for, right? If the distribution of the secrets has small mean entropy, you can of course guess it, and things are not hard. So it's sort of essentially the best possible theorem. Okay, and well, I don't know how much time we have, but if we have time, we'll see the proof sketch of this theorem, stronger theorem. Okay, so with this sort of small secret LWE, let's go ahead and construct a public key encryption scheme, right? And here's what it is. Well, first of all, I have to tell you what a public key encryption scheme is. How many of you know the definition of public key encryption? Good. Okay. All right. Good. About a factor of 5 smaller than I thought, but you know. So here's what I want to do, right? Okay, where do I start? Good. So I want to send a message to Guy, okay? And all I know is a public key of Guy. Is a certain information that Guy published called his public key, and he has the secret key corresponding to this public key, its friend, hidden in his head, right? I can use the public key to encrypt something to Guy, and the only person who can decrypt this is the person with the secret key, which is him, right? So that is public encryption. It was a massive, you know, it was a sort of a landmark kind of achievement in cryptography from the 70s. And there are several constructions of public encryption at this point, but really only a handful. And here's one way to construct it from the learning with errors assumption. Okay. So let me tell you what this construction is. The secret key, right, which is what Guy has in his head, he's not going to tell anybody, is a secret, is the LWE secret, S. And now I'm going to choose it from the small secret distribution. In other words, each coordinate is IID chosen from the error distribution, which is small. Right? Its absolute magnitude is small. What is the public key? The public key, well, is a random set of equations A. So think of an n by n matrix A, right? Over ZQ, Z mod QZ, right? As well as linear equations in the secret S. So A and A times S, right? There's no error at this point, but that's because I want to tell you a construction which actually doesn't work from the learning without errors assumption, and then sort of patch it out. Okay, so it's easier to understand this way. Okay, so that's the public key. Now, that clearly is no good, right? Because I can look at Guy's public key and I can do Gaussian elimination to recover S. But you know what? Between friends, forget that inconvenient fact. Okay, let's keep going. Here is how you encrypt a message, which is a number in Z mod QZ, right? I come up with a random linear equation in a random secret R, which is also small, right? The same distribution as S. I compute R times A, which is multiplying A on the left, right? So R times A, right? And I also take A times S and multiply it on the left. So all I need to do is to look at Guy's public key, which is A and B, right? Compute a random linear equation on the rows of A comma B, right? A concatenated with B, right? Yeah, so R times A concatenated with B. So I'm only using Guy's public key to compute the encryption, right? I don't need to know his secret key at all. And I use this to add the message to the last component of this guy. That's what I'm doing, right? I just rewrote what's on the slides. Yeah, that's the encryption that I sent to Guy. Now the theorem is that if you know, that the thing that happens is that if Guy uses his secret key, he can actually recover.
So then you need another R.
No, I don't need another R. Yeah. Yeah. We'll see. Why do you say I need another R?
You've
We'll
got
see.
a scalar plus a vector.
Scalar. So this is concatenation of columns. Yeah? So here is an n by n matrix.
Ah,
Yeah?
okay, very good.
Yeah, so A and B, they have the same yeah, they're column vectors of the same. A is a matrix, n by n. B is n by 1 matrix. Yeah. So that's what the ciphertext is, right? So now Guy uses this amazing fact, which is that B is equal to, what is it? A times S, right? So R times B, or I guess R transpose B, right? R is a row vector, right? Is R times A times S, right? This can be computed in two ways. You can either take R and A times S and multiply them together, which is what the encryptor did, or you can take R times A and S and multiply them together. You get the same quantity, and that's what Guy is going to do. He knows only R times A multiplied by S. You recover the second component of this thing, subtract it, and you get the message. So this is basically, if you know what the Diffie-Hellman key exchange is, this is exactly what is going on in the Diffie-Hellman key exchange, except you don't work in the exponent and you do the right thing. Okay? Does that make sense? So let me kind of calm down and ask you if any of you have questions, given that I kind of threw you to the deep end with public interruption. Yes?
So we still haven't put the error or the modulus yet?
No, the modulus I did put, because I guess I didn't tell you, all these equations are mod Q, right? So that I did put implicitly, but the error I didn't. Okay, but you see the point. You see what's going on, right? There are two different ways of kind of computing this, this number, R times A times S, which is what I use to mask the message, right? And the encryptor does one thing, the decryptor does the other thing. Good, so let's actually, so this is clearly not secure. Let's put the errors in. The point is that the things work the way they are expected to work, the way they should work. Okay, life is good. Okay, so what do? My public key is now not A times S, but noisy A times S, so A times S plus E, again mod Q, right? When I encrypt a message, I don't compute R times A, I actually compute R times A plus an error, so really it is plus, just add error. Yeah? To the ciphertext, right? And what happens when you decrypt? You do exactly the same thing. You take the second component of the ciphertext minus the first component times S. It's exactly what you do, right? I mean, yeah, that's what I expect, right? So what happens here? Anybody do the algebra and tell me what if I'm good here or not good here? Yes.
Your mu is a single bit. E prime is a single bit.
No, mu is a number for this.
Okay.
At this point.
Okay.
At this point, right? Mu is a number.
Okay.
It's a number in Z mod QZ.
Large modulus. Or
Z mod QZ is a number in Z, arbitrary number in Z mod QZ. Yeah. Good. Anybody? Yes.
In the second line, what are E prime and E double prime?
They are error. They are chosen from the error distribution, right? So there's an underlying LW error distribution chi. I think about it as random in an interval, right? Random numbers in an interval, small interval. Anybody? Ankur is like, why are you guys not getting? Okay, all right. Yeah, so let's try to decrypt this, okay? So R times B here, right, is R times A times S, right, plus R times E, right? So R times A times S kind of goes away here. But then there are a whole bunch of other error terms that live here, right? What are the error terms? I guess you have R times E here, E double prime here, you have E prime times S here, right? These are the error terms. And then you get all these guys plus the message mu. That's what Guy is going to recover when he computes this equation. What the hell? If the message is an arbitrary, you are actually killing a whole bunch of least significant bits of the message. So he's not going to be able to recover the message, right? How do I solve this problem?
R is a vector.
R is a vector.
I can make it a matrix.
You can make it a matrix. You can, of course, make it a matrix.
And that should bring it to the LW.
That I could do it. I could do it. I could do it. Yeah. But at the end of the day, what I wanna say is you need to error correct at this point. That's it, right? I'm saying all you can recover is the message plus noise, right? And I want to actually recover the actual message from it. If the message is an arbitrary number in ZQ, I can't. So fine, so error correct. So here's a poor man's error correction, right? Let the message be a bit, right? And 0 is 0, 1 is Q over 2. That's error correction against L1 noise, right? That's it, end of story. Okay, so this is super simple, right? Okay, yeah, this is clear? All right, good. And a theorem that says as long as these errors are small, so R is a random vector that the encryptor chose. S is the secret key, right? E and E prime are vectors that E prime and E double prime are vectors and numbers that the encryptor chose as well. If this combination is small, which will be, high probability, right? If all these components are small, then you're good. That's you can recover the error. That's it. Proof.
Why is it obvious that this is small? Because R is a bunch of random stuff and you're adding a bunch of things.
Yes. Yes. So, I mean, how do I make it happen, right? I choose R from a sufficiently small, distribution with sufficiently small support, right? Let B be like Q over root n, if you will, right?
So R is also from error.
Everything is from the error distribution. So crucially, you need R and S to come from the error distribution for this to happen, and that's why I actually told you about the LWE with small secrets theorem. If I didn't have that theorem, this wouldn't work. Yeah? Great. Wonderful. Security, never mind. It is, trust me. It's good. Okay? Yeah? All right. Before I move on, any questions? Let me put this back. Yeah.
Just when your demonstration on the board of the reduction, like why were you able to get rid of B1?
Here.
Yeah.
Ask the question again.
Why were you able to get rid of B1?
Get rid of B1? So what I'm saying is the following. I get m plus n samples, m and n, right? So A1 is n by n, A2 is m by n, right? So I get m plus n samples from the LWE distribution, random secrets. I'm going to produce m samples from the small secret LWE distribution. What are these m samples? Well, I use the first n samples to do variable substitution, right? Write S as a function of a small vector, which is the error vector. And then I don't look at it at all. I use them up, sort of, right? And what I get is the equations that come out of here, which is A2 times whatever S was, which is this.
Okay. S had B1 in it, so I'm confused why B1.
Ah, good. So when I do variable substitution, here's what I get. And multiply this guy by A1 inverse. This is what I get, right? But I want to make this into a small secret LWE sample, but then there's this B1 sitting here. What I do is I take it off. I compute A2, A1 inverse B1, subtract it from here, right? So I do use B1 that way, right? I do use B1 to take this off. And what I'm left with is LWE matrix times a small secret plus a small error. So so this, and then I go from here to A2, A1 inverse minus E1 plus E2. Yeah, makes sense. All right. That A is random, right? I mean, yes. If A1 and A2 are random, then it does then it is random, right?
So it's only random but no assumption on distribution.
No, my assumption on the distribution of A's is going to be that it is random, period, right? That's the definition of the LWE problem. Uniformly random, sorry. Uniformly random in Z mod QZ to the power m by n. But each coordinate is random in Z mod QZ.
So A2, A1 inverse is still follow that distribution?
That's right, it does. Yeah. I know what you meant by finite field. Yeah, okay, whatever. Okay, good. Yeah, so it does follow the distribution. So I am actually using the fact that A1 is invertible here, right? But if the first block of A1 is not invertible, just throw it away and do the second block. Okay, so this guy is invertible with high probability, and quickly I'll get to an invertible A. Yeah. All right, good. Good questions. All right, so here is, let me move on to the second application, which is to the hardness of learning Gaussian mixtures. This is work with, it's work that originally was done by Bruna, Regev, Song, and Tang, and we improved this with Aparna, who's here, and Nikon Rafa. All right, so this is what I showed you in the party trick in the very first slide. Two distributions, right? The Gaussian on the left, and the Gaussian pancake distribution on the right. So let me make it a bit more precise. So here is the distribution, right? It looks, if you squint at it, it looks like the LWE problem with the following differences, right? So now the problem kind of comes to your world from my world. My world was a finite field world. It comes to your world, yeah? What are the equations here? The equations are Gaussian equations, right? So each AI is drawn randomly from sort of unit covariance Gaussian. I picked my secret uniformly from the sphere, right? Unit norm sphere. I give you noisy linear equations. AI in a product S plus an error. The error kills the least significant bits, in a sense, as before. Then I'm going to give you these equations mod 1. What does that mean? I compute this real number, AI in a product S plus EI, right? I ignore its integer part. That's what it means to compute this mod 1. Right? I just give you the fractional part of this equation, right? So I am throwing away the most significant bits and the least significant bits, so I'm still in that sort of regime, in a sense, right? Yeah, is that good? So that's the continuous LWE distribution, the thing I wrote inside the box, right? There's a scaling factor which we'll get to later. The assumption is that the problem is to kind of distinguish this from IID Gaussians, right? Where AI is still Gaussian and B sub I, well, actually B sub I is randomly chosen from the torus, right? So B sub I always, the second component of this distribution, the one on the top, always lives in the torus, right? Because I took a number and I just looked at the fractional part, so it always lives in 0, 1, right? So instead of doing that, I pick BI randomly from the torus, and that's the second distribution. And the assumption or the problem is to distinguish between these two distributions. Right. There are all sorts of issues with finite precision and so on and so forth. I'm really not going to get into. You have to solve them, but it's very uninteresting, and not going to get to it. Okay. All right. So in pictures, this is what it is, right? That's a Gaussian, right? And I colored the Gaussian, depending on what the Gaussian in a product with the secret direction plus noise is. Right, so that's the CLW. Good. So far so good. Yeah. Let me tell you now what this gamma is, right? So the gamma is sort of a scaling parameter that tells me how many most significant bits of AI in a product S plus EI do I forget? Right? If gamma is large, I'm forgetting a lot of bits. Right? I'm scaling this guy up, and then I'm saying, let me only take the fractional part, so I'm losing a lot of bits. Right? Gamma is small, I'm losing fewer bits. That's what it is. Yeah? Is that reasonably clear? All right. Correct. In the picture, it controls what I'll tell you in a second. How thick the bands are is controlled by beta, right? Actually, beta over gamma. I'll tell you in a second. So here's a slightly different version of LWE, which is what I'll use to show hardness, which is a homogeneous CLWE problem, which is basically saying, let's come up with a CLWE distribution, but conditioned on the second component being 0. Okay? So in other words, draw AI, like sample AI, like rule rejection sampling, so that this condition is actually true, right? And that is the homogeneous CLWE distribution, which looks like this. So now back to Sleel's question. The bands, the width of the bands is beta, essentially, the amount of the error divided by gamma. And the separation between the bands is 1 over gamma. So in other words, there are gamma bands in this, gamma pancakes in this distribution. Right? Does that make sense? Because in one direction, right, this guy looks like a Gaussian, so its spread is constant, right? And the distance is 1 over gamma, so there are gamma bands, roughly gamma bands. Yeah? So that is the continuous homogeneous CLWE problem. And the theorem from Bruna et al. Is that there is a reduction from CLWE to homogeneous CLWE. So if you can solve the latter problem, you can solve the CLWE problem. Okay, good. So now, Gaussian mixture learning and how is this related? As you can probably see right away, this is very, very Gaussian mixtures, right? Here's the Gaussian mixture learning problem. Now I'm in your territory, right? So you're given a weighted mixture of Gaussians with means mu I and covariance sigma I, and you're supposed to either find the parameters, or you're supposed to come up with a function that estimates the density of each point, or you're just supposed to distinguish the mixture of Gaussians from, let's say, one Gaussian. One standard Gaussian. In fact, what I'll talk about is the last version of the problem, which is the easiest algorithmically, but I'll show hardness. So that's actually better to show hardness of the distinguishing version, right? Does that make sense? Yeah. Long line of work, people in this room and several others. The best algorithm I know, and you can correct me with parameters if I'm correct, says the following. You know, if you have a mixture of a fixed number of Gaussians, like a constant number of Gaussians, G Gaussians, right? You can learn them, in fact, even in the strongest sense, right? In time n to the G, or n to the f of G, n to the some polynomial in G. Anko, do you know what f of G is? To the G,
But you know, if you have something like, you know, they exist on roughly the same scale,
right?
Then it's you know, much better at some poly in G.
But some poly in G. Sort of, for example, well-separated Gaussians.
So I mean, it has to do with, like, you know, you could in principle have Gaussian mixtures which, like, you know, the variances degrade at some exponential rate, and then that's exactly where things get difficult.
I see.
Good. On multiple scales.
Good.
Good.
Good. The hard instance I'll come up with is actually a relatively nice, well, actually, I'm not so sure, but we'll see. Okay, so f of G is at least linear. There's a hardness result for this problem by Elias, Daniel Kane, and Alistair Stewart, who show that this is actually, I don't want to say tight, there's an n to the omega G lower bound in the statistical query model, right? For this problem. More recently, Bruna et al., in the paper where they defined the continuous LWE problem, they showed that, so you know, like, what does an SQ lower bound mean? It says certain algorithms cannot solve this problem better than, in time better than something, right? Here is a very different kind of hardness result, which says that, which is a sort of a conditional hardness result, right? Which says that, you know, if a certain problem is hard, if lattice problems are hard, the shortest vector problem is hard, quantumly hard, turns out, then there is no polynomial time algorithm that solves, that learns a mixture of sufficiently many Gaussians, like root n Gaussians, right? Yeah, that's what the result says. Yeah. So there are two things that are non-tight about this result. One is the quantum, which you may or may not care about. But the other thing, the more sort of interesting thing, is that it only says that learning root n Gaussians, mixture of root n Gaussians, is hard, whereas the algorithms work for a constant number of Gaussians. So what is going on in between? All right. So here is how the two problems relate: homogeneous CLWE and Gaussian mixture learning relate. HCLWE is really a mixture of Gaussians. Right? How many components? Of gamma components, and this is after sort of truncating it. Say again? What is the homogeneous part? You pick a Gaussian, but condition it on gamma times AI in a product S being equal to a Gaussian, plus the error being 0. Right, so think about the continuous LWE distribution here. Yeah, here. Pick out only the, I don't know, the green band, right? That's right. Okay, so this guy is really a mixture of Gaussians, and what Bruno et al. Showed is that the hardness of the continuous LWE problem with parameters beta and gamma and dimension n implies the hardness of learning mixtures of about gamma well-separated Gaussians, n-dimensional Gaussians. That's really, so more or less follows from the definition of the problem after truncation. So I'll show you something even better. I'll show you a result which says that you just need to assume the classical hardness, classical worst-case hardness of shortest vectors, and you can get the hardness, the average case hardness, of course, of learning Gaussians, of learning how many Gaussians, essentially constant. Turns out to be log n, right? Omega log n Gaussians. Right. So I am actually cheating here a little bit. Bruno et al. Assumed the polynomial time hardness of computing shortest vectors. I'm here assuming the sub-exponential hardness of computing shortest vectors to get the tightest possible result. But then again, if you remember the picture from before, the shortest vector problem is hard, 2 to the n to the 0.99 approximation factor. So, yeah. Good. So the way I'm going to show this is I'm going to show a reduction from the finite field LWE, the LWE, the real LWE problem that I defined, to continuous LWE. So once I show this, and I have a worst case to average case reduction for LWE, which I stated but I didn't prove to you, right? Put them together, you get the theorem. All right, so again, this is the picture. Bruno et al. Showed that root n Gaussians, learning root n Gaussians is hard. We can, under the same assumption, under polynomial assumptions, you can improve the root n to n to the epsilon for any constant epsilon, right? So this is kind of like assuming the same thing. You can actually improve root n to n to the 0.0001, right? And if you want to make if you're willing to make a stronger assumption, which is sub-exponential 2 to the n to the 0.99 hardness, then you get hardness of learning log n Gaussians, superposition of log n Gaussians. Yeah, and the best known is constant. Really, like, where is the truth? I don't know. And let me I am actually going to try to prove this. "15 minutes. Okay, so it's sort of the decision time. You know what? I am actually not going to try to prove this theorem because you are statisticians. Okay, so you can either simulate in your head the proof of this theorem or look at the slides. Okay, but what I am going to show you is a few more cool facts which hopefully you cannot simulate. Okay. All right. So this is what it is. Open problems. Okay. So I don't know. Can you show a tight hardness result? I mean, like what is log n versus constant? You may not care, but it bugs me. I don't know. It really bugs me. Okay. So what is the truth here? We have a tight SQ hardness, right? But we lose this log n factor. Like, what is going on? Sometimes, when you try to prove lower bounds and you work hard and hard and hard and hard and it doesn't work, maybe there's an upper bound. I just don't know. Right? Maybe there's an upper bound that is not an SQ algorithm that actually uses crazy thing out there. Let me throw it out there: basis reduction. Right? I just don't know. I don't see how that will come up. But yeah. Are there other sort of natural connections to learning problems? Yeah. Okay. So I'm going to skip this. The proof that LWE reduces to CLWE, again, yeah. Okay, so let me finish by telling you two cool properties of the learning with errors assumption, right? One is the worst case to average case reduction, and I really won't, it'll take me an entire lecture. In fact, it takes me a lecture and a half to actually show the proof of regF's worst case to average case reduction, but I'll show you a cartoon. Okay, hopefully the cartoon already tells you, like what really is going on here. And in fact, I will actually show you a worst case to average case reduction, not from SVP to LWE, but SVP to CLWE, which is actually kind of nicer to see even. Right? So here's how the proof works. Again, I'm given a lattice. The lattice has either short vectors or not short vectors. So the shortest vector is either small or not, and I want to distinguish between the two. And I am going to create from these lattices, worst case, arbitrary lattices. In one case, I'll create a distribution, which in one case will be LWE, CLWE. In the other case, it will be Gaussian. Okay? Again, this is a cartoon. It's just a taste. There are lots of things that are missing here, but All right. So here it is, lattice. Okay. Great. Okay. So gap SVP, sort of the decision version of the shortest vector problem, sort of says that lattices with n short vectors, a full rank, full dimensional kind of set of short vectors, like so here, like 2 short vectors, are indistinguishable, are hard to tell from ones with n minus 1 short vectors, and in one direction, stuff's long. Okay. You are going to laugh at me. What do you mean? I mean, you can tell, but remember, you're living in n dimensions, not 2. Okay. So this direction is arbitrary. Okay, and this actually is equivalent to the decisional shortest vector problem, which is actually the dual of this, right? So the decisional shortest vector problem says that you have one short vector and everything else is long. I'm saying I have n minus 1 short vector and one guy is super long, right? So this is sort of the dual of it. In fact, it follows from duality, the connection between these problems, the lattice to its dual. Okay, so this problem is hard in any case. What am I going to do? What is the reduction going to do? The reduction is going to add a small Gaussian to a randomly chosen lattice point. If you don't sort of nitpick on what randomly chosen lattice point actually means, randomly chosen from this slide, let's say, right? Here's what it looks like. Here's what I take one point and add a Gaussian looks like, right? Here's what adding a Gaussian to a random lattice point looks like, right? It's a mixture of Gaussians, one centered at every lattice point, right? You see what's going on, right? This thing, as soon as the Gaussian width is large enough, this covers the space. You get a really like a, if you squint your eyes, it looks like the uniform distribution. Right? In fact, this is actually formal. It's a smoothing lemma of Micciancio and regF, which is sort of a workhorse in sort of lattice space cryptography. What this says is that, well, actually, maybe it's not obvious, okay? Maybe it's not obvious. What do you expect? Okay, so you take a random lattice point, okay, you add Gaussians. Start with a tiny Gaussian. Okay, that doesn't cover the space, obviously. You increase it to half the shortest vector, right? So then it starts kind of covering sort of, each sort of line in the lattice, right, in each direction. Then you increase it to the length of the nth shortest vector, nth linearly independent shortest vector. Then it covers everything, right? It's sort of it seems to cover everything. But why is it uniformly random? Maybe it covers some areas of space better than others, right? More than others. What is clear is covering. What is not clear is uniformity. Right? So this is a statement that you think, well, at first sight you think it's obvious. Then you think again and say, well, wait a minute, maybe there's something funny going on here. It turns out to be true. Right? So this is the smoothing lemma. It says that you choose x from a Gaussian. If the parameter is bigger than the nth shortest vector of the lattice, so it's lambda n, right, times some factor, which is root log n, essentially, over epsilon, then the resulting distribution is epsilon close in variation distance to uniform. Or actually, more honestly, there's no notion of choosing a random lattice point. So what you do is you pick the Gaussian from the origin, and you reduce it modulo the fundamental parallelepiped, right? So you do it. So that is what it means to, right? choose this, then you say, okay, I'm going to cut this and put it here, I'm going to cut this, put it here. I'm going to cut this, put it here. Right, so you get a distribution on the fundamental parallelepiped. At least that's finite, and I can actually talk about uniform distributions on the fundamental parallelepiped, and that's what actually it is close to. Right. So this is actually a surprising statement. It's not obvious at all to me, but turns out to be true. It uses sort of deep theorems from geometry of numbers to actually prove it, and Fourier analysis for good measure to prove this. Okay, so in any case, that's what happens. Now let's look at what happens to this lattice. Okay, so I do the same thing, the same width of Gaussian, right? What do you see here? Lunchtime. Pancakes, right? Pancakes in what direction? In the direction of the secret vector, of the long vector, right? Now, of course, you can rotate this randomly, and the direction will become random, right? You can also scale it. It turns out that that takes a little bit of care to a unit vector. That's not entirely obvious from here, but you can do it. Okay, so this is the worst case to average case reduction. Yeah, what I just did is I took a lattice, I created one distribution or the other. If the lattice had n short vectors, I created the uniform distribution, or it'll turn out Gaussian. If it has n minus 1 short vectors, then I create a pancake distribution. That's it. Lots of details under the rug, but this is the core of the result. Okay, number 2, I have 7 minutes. Let me end with showing you the robustness property of LWE, which is what I stated before, which is take LWE, change the secret distribution to whatever you want, as long as it has enough min entropy, right? You're good. So here's the problem, right? The only difference is S is chosen from some distribution D. It doesn't have to be, the coordinates don't have to be IID or whatever, I don't really care. Okay, so this is the theorem with a star. Yeah, so this problem, if you can solve this problem with under any distribution, essentially, any distribution D, more or less, that's where the star is, then you can solve the real LWE problem, the LWE problem with uniform secrets, for example, right? In a related number of dimensions, right? So you would expect that as the distribution has less and less entropy, right? The problem becomes easier and easier. So being able to solve it, impresses me less and less. In other words, it lets me solve lower and lower dimensional LWE problem, and that is characterized by this. Right. Good? That's the theorem. Yeah? Here's the proof. Okay, so do a reduction, right? You solve entropic LWE for me. This is the entropic LWE problem. I'll solve the real LWE problem. Okay? I'll tell you the idea. 2 ideas, really. Idea 1, you know, this distribution S, right, that I pick S from D, that I pick S from, all I know about it is that it has min entropy. Okay? I don't know anything about it. It's not IID, nothing. Right? All I know is entropy. What do I do with a distribution which only has entropy? You know, like that's all I know. What do I do with it as sort of TCS people? You know, what can I do with it? I mean, like I don't know, I can rotate it or whatever, but you know, like I just don't know. I mean, one funny distribution becomes another funny distribution. Like, thank you very much. What do I do with distributions that have entropy? How can I play around with them? Too close to lunch? Compress. Compress is a great answer, right? Compress to a uniform distribution, right? You can do randomness extraction. So this is the entire field of TCS that does precisely this, right? It takes a distribution, which, you know, a string from a distribution which has min entropy, and outputs a condensed string, a smaller string, which is uniformly random or close to uniformly random, right? How big a string can you output? It turns out that all this work of like, you know, starting from Zuckerman, you know, 20, 30 years of work shows that you can essentially extract the entire entropy from a string, from a distribution. So that's randomness extraction, and that's what we want to do here. Even better, there are very simple ways to do randomness extraction. There's this beautiful lemma called the leftover hash lemma of Impagliazzo, Levin, and Luby from the 1990s, which says that, you know, you take a vector from a distribution which has entropy, multiplied by a matrix, a random public matrix, right? So I pick a random matrix, I tell you what the matrix is, and I do matrix vector multiplication, right? Of a sufficiently small size. The matrix has to be compressing, right? It actually extracts entropy. The output of this matrix vector multiplication is TV distance close to uniform. Right? It's a beautiful, beautiful theorem. In fact, it's a linear extractor, right? What's even better than randomness extraction is randomness extraction by a linear function. Okay, that's what we are going to do. Okay, so idea one. Okay, so why doesn't this work already? Because if A were a matrix, which is sort of a short matrix, right? It is sort of k by n, where k is actually much smaller than n, then this would already work, and you would get sort of information theoretically, statistically close to uniform, right? But it isn't. A is tall. A is outputting tons of samples. That's why left-of-hash lemma doesn't work as is. So here's the first idea. What if you can replace the random matrix A by a low-rank matrix? Okay, so low-rank matrix is B times C. B and C are rank k, approximately, right? How many people think I can do this? Indistinguishability here means no polynomial time algorithm can tell if I'm giving you the one on the left or the one on the right. This is ridiculous, right? You can compute the rank of a matrix, or mod Q to, over finite fields, right? So I can't do this. I can't do this. But you know what? Between friends, what's there? Let me do it anyway. Okay? So let me do this. What is the consequence, right? If A and B times C, they are indistinguishable, then so is A times S plus E and B times C times S plus E. Right? It's just polynomial time computation on two indistinguishable distributions produces two indistinguishable distributions. Now I apply the leftover hash lemma. I look at C times S. There's a hidden low-dimensional subspace C inside A. That's how I set it up. So C times S is now a truly random vector. So I get B times a much shorter vector of length roughly k, the entropy. And this guy, it looks like the LWE distribution, which is random, which is indistinguishable, computationally indistinguishable from random, right? So I used LWE twice. One to argue that these guys at the very end, and to argue that these two guys are indistinguishable. That's what I want to do, right? At this point, it's not true. So how do I fix it? LWE tells me that an approximately low-rank matrix is computationally indistinguishable from a random matrix. That is the core, that's the essence of LWE, over a finite field, right? Over a finite field, B times C, sprinkle in, I don't know, Gaussian noise or like a uniform noise or whatever, looks indistinguishable from a random matrix A. This is identical to the LWE distribution. In fact, maybe you need a little bit of work to show this, but you can. Okay, so now I have it. Now step one is actually a real step. We don't have to be friends anymore. Okay, so this is it. That's that. Yeah.
What scale of noise do you need?
Whatever the LWE distribution kind of dictates, right? And for the reduction to work, you need the noise to be like polynomial in n factors smaller than q. Like q over root n should suffice. So there is that detail, right? And you'll see why in a second. Okay, so this is idea one prime, right? And what do I do? So now my idea two actually works, but doesn't work as well as before, right? What did I do? I replace A by B times C plus n, right? Approximating low-rank matrix times S plus E. I get B times C times S, right? Which I want to extract. So I want to say S is actually entropic. I can extract. But then it's not as entropic as before because there is this other matrix, this other vector n times S that lives there, which might actually reveal the entirety of S. Right? I have to somehow argue my way through it. There are a couple of different ways of doing it. Here is one way, right? You can, of course, decompose a Gaussian. Let's say E is Gaussian. This is where I'm using the fact that E is Gaussian, into two smaller Gaussians, sum of two slightly smaller Gaussians, right? And now what you want is that I give you n times S plus E2, right? Yeah? S still has entropy. And if S still has entropy, I will apply the leftover hash lemma just as before, right? And this you can argue one of two ways. You can either set the error to be large enough that it kind of floods this n times S, right? And for that, n and s have to be small norm, right? N is small norm because it's the LWE distribution. S, I'm going to assume that it's small norm. So that's the kind of distributions I'll talk about. And E2 is a large enough error that it floods the n times s. Then I can apply Lepto-Wash lemma. The more kind of general statement here is something that Zvika and Nico, Brakerski and Dotling came up with, which said, look, all I need from the distribution is this condition, right? This characterizes when the reduction would work. And again, if S is chosen from a binary support distribution or a sparse distribution, all of these things would fall in this category. Right? Good. So that is the entropic LWE thing. So let me kind of, I'm 3 minutes over. Let me summarize. Right, we saw the learning with errors problem. We saw algorithms for it, like 2 algorithms. We saw a cryptographic application and a statistical application, so to speak, application to hardness of learning Gaussian mixtures. Then I showed you a cartoon of the worst case to average case reduction and the entropic LWE hardness, right? So that's what we showed. So hopefully this is enough kind of information for you to, if you're interested in it further, to start digging around a bit more. And there are tons of material online. There's an entire class that I taught at Berkeley a couple of years ago during the pandemic. Hard memories, but that's what it is. There's Chris Peikert's survey on LWE. There's a website with tons of links to courses, surveys, and so forth, and papers. And yeah, thank you.